So introducing our next speaker. They are I think, professor at Dartmouth. No, an adjunct professor at colleges up north from here. They're a excellent hacker. A very long-time friend of mine, personally. Long-time friend of, I think, many of yours as well. A very good teacher. I think I mentioned that already. They weigh around 40 pounds. They wear a collar, but they're into it. Our next speaker is actually going to be Ghost, who you can see here. And then we've actually brought in Kai as a translator, so it's going to be driven that way. But the bulk of the work, just for the record, was.
100%.
Boop. All right, please give it up for Kai and Ghost.
Howdy, everyone. So I am here to talk about implants. So I'm Kai. I'm a security researcher and a student. I also teach at Northeastern and BU sometimes. If anyone here is hiring new grads and needs a really talented hacker, let me know. I have lots of students. And one important thing is I am not a programming languages person, and I don't know how compilers work, so we're going to get through this together. So I have a couple of things that I want to talk about, but one of them is just me popping off about how cool Darksword is. It got leaked, and I think that it was properly appreciated publicly, but I still want to ramble about how cool I think it is. I also want to talk about how one weekend just kind of being bored after writing a CTF and then trying to solve the CTF that I wrote in a lot of different ways has led me to a point where I will hopefully, fingers crossed, have a paper I can publish so I can stop being a PhD student. So I'm going to talk a little bit about ELF files. I'm going to talk a little bit about LLVR. Oh, no, Ghost. Come here, Ghost. We're going to write a loader. We're going to write a really shitty implant. And hopefully I will get through all of this in the time that I have. I'm going to keep this up so that I don't lose track. Ghost, come over here. Okay, so a couple of other things. I did not actually write an LLVM parser. That seemed like a lot of work, and I asked Claude to do it, and it did it on the first try, which was good enough for me. There's probably a lot of problems in it, but because this isn't going to be used for anything important, I thought that was fine. Also, whoop. All right, Ghost, come over here. Down you go, good girl. So good. So yeah, use LLMs for a lot of things. So I wrote a CTF sometime last summer, and it was a pretty straightforward puzzle. You ended up getting a read-write because you messed around with a particular matrix operation inside of a bad linear algebra library. From there, you went through and hijacked an exit handler, and you could go through and do whatever you want. So the only thing that made it kind of tricky was I turned on a bunch of the mitigations and ran it in QEMU. Nope. All right, Ghost, you want to go say hi? Go say hi, Ghost. It's okay, girl. But yeah, so the way that you solved the CTF was pretty straightforward. And then I kind of got bored, where I was like, all right, well, what if you don't just want to pop a shell? What if you want to do something with it? And I started just scrolling through a bunch of different libc functions and came up with a couple of ideas. But one of them was just looking at the way that coroutines are implemented, and none of this is new. Jump-oriented programming is a pretty known well thing at this point. But setcontext itself seemed really, really funny looking, where it restored the entire register state, not just a jump with some register control, you control all of them. And I thought, is this enough to go through and just build an entire program with? The answer is not quite, but if you combine it with a couple of other functions in libc, you can do some pretty funky things. So we're going to be focusing a lot on what can you do if you're only playing around with libc. So just quick show of hands, who here knows what ROP is? Okay, who here knows what BTI is and shadow stacks and CFI and mitigations like that? Okay, so TLDR, there's a handful of mitigations that have been released in the last decade or so that ostensibly kill ROP, not actually in practice because a lot of this stuff wasn't really rolled out. But the idea is it's a lot harder to jump into the middle of a function at this point. So you basically need to jump to the start of a function, and it needs to be the right kind of function depending on the type of CFI that's on. But at its core, I thought, all right, well, what if I'm only playing around with functions in libc, right? So it's kind of like I'm going to build like a ROP compiler-like thing, except no jumping into the middle of functions, only two functions. So this kind of set off like, I don't know, me obsessing over something instead of doing my actually work for a little bit. But then it kind of became like, all right, well, what if I try to generalize this, right? Because for a while, you think about exploitation, you think about, well, on harder targets or modern systems, there's lots and lots of sandboxing and lots of isolation. So one bug probably isn't going to let you compromise a system. So you need a bunch. And you need some way for the first bug to run the second bug. And normally that just means shellcode. And if you can get shellcode in a running process, that's awesome, because then it's really, really straightforward to run the next portion. It also makes them really modular, which makes it easy to swap in and out components. So, but what if you don't get shellcode? And me trying to generalize this of, well, what's this sort of like superclass of things that lets you like bootstrap different programs on different stages? So a couple of examples of like, I don't know, me trying to generalize this, well, what if you just have a read-write, or what if you just get syscalls, or is Turing completeness enough? And Turing completeness is one of those things that's like a fun flag to get, but simulating a machine and actually making syscalls are two different things. So just keeping it super easy. Let's say you get like RCE on a server and you want to escalate to root. Most root exploits are just a bundle of syscalls. So you need to be able to make syscalls. And I kind of want to go through and like distill this down to, well, what is the minimum set of capability you need in order to go through and run your next program? And I'm just kind of calling this handoff-oriented capabilities because, again, I need to write a paper and I need to make up definitions. But it's just weird machine stuff, right? Like there's nothing like super new here. But it's me trying to go through and just like catalog this stuff, right? So why bother with a generalization if you can just get shellcode? And it turns out you can't on a lot of like really big, hard systems. So I also want to have a quick disclaimer. I don't know that much about iOS, like at all. But I was definitely inspired looking at like what Darksword was doing and being like, why the hell are they jumping through all these hoops? Like, why not just do this? And it's like, oh, they can't do that. And looking at the specific way that that was implemented inspired a lot of this like tinkering around with just functions. So the other thing to keep in mind is that when you go through and run a bunch of exploits, you're probably not just trying to cat, slash flag. You probably want to do something. And normally you would think about the final handoff point as just being a native binary or shellcode, and you're done, right? You run your exploit, you run an implant, and then you're a happy camper. Except you might not actually be able to run an implant in some of these systems. So to sort of catalog what I mean by like a hard target, you can sort of like take two minds of this. Like one of them is like how hard is it to actually exploit this thing, but also like how many other people are looking at it. And I think like I'm borrowing a quote from Ian here just saying market conditions. But at the end of the day, I'm really thinking about iOS here. And the reason I'm thinking about iOS is because Apple is like a pretty cool company that has a really cool security engineering team. And a lot of the mitigations in there, like I don't even know them all. There's like too many to keep up with. I gave up, too many acronyms. And a lot of the mitigations are like super interesting. So some of them that make it like really hard is even if you get a kernel read-write, they got rid of the thing that manages page tables and took it away from the kernel and put it in Apple's version of TrustZone. So you can't really mess with physical memory as easily anymore. The thing that basically dictates what process is allowed to do what are its entitlements, and the thing that basically stores what process has what entitlements, or all the code that like checks it, lives inside of something called TXM. I think it's trusted execution module, I don't know. But it's basically really, really hard to mess with entitlements, and it's really hard to mess with page tables, and as a result, it's a lot harder to get native code execution on iOS. Like even if you have a kernel read-write, you're kind of stuck if your process doesn't have JIT, and there aren't many processes that have JIT, and the ones that do are super heavily sandboxed, so it's just kind of a bad time all around. So this is kind of extra cool because Darksword was one of the first examples of an implant and an exploit that was kind of bundled together, thrown at a system, and then didn't do anything with native code. So iOS is like extra hard because the category of bugs that you need in order to go through and run a native implant, they're really, really hard to come by. Like you basically need like a triangulation style thing that just kind of ignores the MMU or the IOMMU. And yeah, good luck finding those. So what do? We're kind of stuck, right? So we have some options. In order of how unlikely you could try to bribe Apple, which I don't have enough money to do that. You could probably bribe a vendor. sure, someone would be able to do that. You could probably steal signing keys, but that's also super hard. And then once that signing key is stolen and gets caught in the wild, they get rid of it and you're back to square zero. So the last one is you just kind of accept that you're not going to have native code. And that's like a kind of funky thing to think about. Like you spend all this time building something that gets you into a device and you're like, yep, I have compromised it to almost the like highest level that you can, and you still can't run any programs. That's kind of cool, right? So Darksort is the first example of like a caught in the wild exploit chain that like actually does this. So yeah, I think someone else talked about it earlier today, and they probably did a much better job than I'm going to. But just to keep it very, very brief, I think it was like a WebKit, like RCE and sandbox escape with an LPE. It was all written in JavaScript and stapled to it was something called like RCE module or something, or PE module or whatever it was, that effectively like wired up a native bridge to JavaScript so that once it was time to go through and do the post-exploitation, you could write the entire thing in JavaScript, which would then jump to wherever the native bridge was wired up. So that's kind of wild to me, right? Like you write the entire thing in JavaScript, and just the like hoops you need to jump through to get even something working on iOS is crazy to me. So why did they write it in JavaScript? Because you have an interpreter, and if you have a bug and you can wire up a native bridge to that interpreter, you basically have something that's almost as good as a native executable, which is pretty cool. Why else JavaScript? A lot of bugs, for now anyway, who knows? MIE is very, very scary. But also it lives inside of like basically the dilib that implements all of JavaScript for like Safari is inside of the shared cache, so like technically any process can load it, but nowadays not any process can use it as of like 1 or 2 versions ago. So, okay, I think that, you know, unless something like radical changes, this is probably going to be the norm for Apple forever, and maybe if Android gets like harder or Windows gets harder, this will be the norm for them too, but I don't think so for a number of reasons. But even for something like Darksort, like Apple's going to go through and mitigate it, which I think they already have, and this is just going to kick off like another cat and mouse game where it's, okay, well, what other options do we have? So I kind of want to think about like, I don't know, what exactly the state of an implant and an exploit is going to look like on some of these like really, really ridiculous targets like iOS. And for that, I have this idea that, well, at a certain point, all exploits are going to have the implant bundled together, and they're all probably going to be kind of interchangeable at some point. Like the implant's not going to run without the exploit, and the exploit doesn't deliver an implant. The exploit is the implant. Maybe this is just like dumb semantics, but yeah, I don't think we're going to have easy buttons anymore. I don't think you're just going to be able to drop dilibs anymore. And with the pace at which Apple goes through and catches stuff in the wild and patches it, and also comes up with more mitigations, like, yeah, it's going to be kind of crazy. Also, memory integrity is really, really spooky. So with all that said, what are we kind of stuck with? Well, I think I kind of already rambled about this, but basically, you're not going to get executable memory, so you got to make do with what you got. So how are we going to deal with a lack of shellcode? We're not going to get executable memory, and we need to do something. So the answer, I think, is we give up and cache out. The second one is you find an interpreter that doesn't have a native bridge and wire it up, kind of like what Darksort did. If you're on something like Android and they somehow make it more difficult to run shellcode, which, again, good luck with that. I'm going to eat my words in a year, I know it. You can find an interpreter that already has a native bridge, and then, okay, you basically have native code execution again. So that would be something like Java on Android. Another example is you find an interpreter and then wire up a native bridge yourself. I'm using scare quotes because this is something that's not like a programming language. These are like your JBigs of the world, or your JBig2s of the world, right? The other one is you just live inside of a process that has a JIT. I guess WebKit technically has a JIT, and the sandbox is kind of obnoxious. But if you can somehow mess around with the JIT, maybe you could run the rest of your stuff and just live in there. Sounds kind of annoying. You could also just find some really, really useful objects, and then as soon as you use them, Apple's going to be like, okay, we're going to make it harder to use these. Maybe you go through and build a jump compiler. That also sounds really painful. But all of these kind of have one thing in common. It's go find something and just use it like an interpreter and wire up some sort of native bridge. So today's talk is going to all be about, all right, like, let's try doing that. So also, I'm like, again, not an iOS expert, so we're going to pick something that I know a little bit about, and that's going to be like Linux on like AArch64. We're going to pick ARM. we're going to pretend that it's a harder target and basically just restrict what we're allowed to do. And we're going to try to build something that conforms to those artificial constraints. So namely, no code execution in Rx memory, basically only data-oriented stuff. We're going to use a QEMU lab that has BTI and everything else turned on, so you can't just jump into the middle of a program or like a function, so no ROP. And yeah, then we're going to try to build a compiler on top of that. So yeah, so basically this kind of restricts us all to, we're really only allowed to use function gadgets inside of libc, and we're also not going to go through and overwrite like executable memory. So for anyone who's like, oh, what about proc self-mem? No, we're not using that. We're going to go through and just build something from scratch. So just quick show of hands, who here knows ARM calling conventions, or I guess ARM v8a calling conventions? Okay, good detour. So there's a bunch of general purpose registers. The ordering of them is much more sane than I would say on Intel. Yes. The first 8 is where your arguments go. X0, where the return value goes. So if you call malloc and it returns something, that return value is going in X0. So also the way that you go through and jump to a function and then jump back is kind of nice. You basically have a branch, which is an unconditional jump, and then you have a branch with link, which is, hey, I was just here. When I pop back, I'm going to store this return value inside of this register. Please bring me back here afterwards. So that's kind of also nice for chaining things along as well. Everything else you don't really need to know, but the only other thing you need to know is that we're going to be talking a lot about coroutines. So you have a regular thread, it's running on a system with a kernel. The kernel gives you a little bit of time to run, and then it goes, all right, your time is up. My CPU, you can't have it. And I'll give it back to you maybe at some point when I schedule you to run. So this is like preemptive scheduling, right? Then you have cooperative scheduling, which is you have a bunch of things that are basically sharing a thread or a collection of threads, and you context switch between the same thread without jumping into kernel land. So a context switch is just changing the register state. So this is not, precisely accurate across every single green thread or coroutine implementation you can find. Like Go routines do weird things, like C++ coroutines are super weird. Grand Central Dispatch is a mess. But on glibc, you basically just have a handful of functions that are designed for implementing coroutines, and one of them is called setcontext, which takes as its first argument the virtual address of a ucontext t, which is the register state, which for anyone who's ever played in a CTF before, that's a pretty sick gadget to use. It doesn't just like move things around. It's no, like I'm going to define the entire register state, and then I'm just going to set everything. That includes the program counter. So that's kind of cool. So I built out a whole thing around this called context-oriented programming. Again, I think this counts as jump-oriented programming, but I feel like I kind of went overboard with it, so I'm going to call it something, and also, papers. So
you're an academic, right?
Yeah, I can just, make shit up. So cool. So I'm just calling it a super gadget. It's like kind of ridiculous and super, super powerful. But in and of itself, it's not actually enough, and I want you guys to think about why it's not enough. So I can jump anywhere I want once, but now I got to figure out how do I jump to the next thing, and how do I get arguments from that thing, and then how do I use this gadget to go through and do something like, I don't know, arithmetic or conditional logic or branching or whatever. But just keep in mind, the key data structure here is a ucontext t, and this is just the entire thread state, which is super, super powerful. So how do we go through and basically chain together these dispatches? So one option is to go through and search for something that will allow us to go through and, I don't know, like call setcontext multiple times. And as it turns out, the authors of all these coroutine helpers actually added a bootstrap called startContext, which does exactly this. So if you were using the library in the sort of intended way, you set the UC link, which is the address of the next context that you're going to jump to. So now I can call a bunch of functions in a row with all of the arguments controlled. So startContext is pretty useful. This is how you would actually use setcontext in general. The UC link is set as one of the values. But the actual trampoline that does this is it just jumps to, it just jumps to x20 and then eventually brings you back to setcontext, which that's pretty awesome. So now I can go through and just call a bunch of functions over and over again. Like think about how I might exploit this. I build a context tape of context objects. I wire them all up, a single call to set context, then it jumps to start context and goes set context, set context, set context, so on and so forth. So it'll just keep on running. So that's also pretty sick. So now we have multiple dispatch. And the one question that you should probably be having is what about CFI and BTI? And it's not on. There are lots and lots of places where these mitigations just don't exist, and it doesn't necessarily make sense how you would go through and add them, just sort of why they exist. So the actual mitigation here is just get rid of it because nobody uses it. I left it like a BPF trace running on like a bunch of different servers looking to see if any of them used set context, and none of them do. And I know that Apple and a couple of others go through and basically like identify these weird gadgets or like anything that's used for exception handling, and they'll add like cookies or little like exclusive OR values or some pointer mangling BS, and these are all things that can be subverted with a read-write though. BTI and CFI a little bit harder. So yeah, it's just not on. And this is kind of like a nice, like, I don't know, aside of oftentimes there are these like mitigations that show up and you're like, damn, this mitigation looks really hard. I wonder if there's anywhere that they just didn't put it. And then oftentimes there is, and you go, great, I don't have to fight the mitigation because the mitigation is hard and I don't want to deal with that. So, okay. How do we actually program this though? We can call lots and lots of functions back to back in quick succession. I need to be able to go through and branch. I need to be able to, I don't know, malloc and then capture the argument. And can anyone see why this doesn't work out of the box? If I destroy the register state in between successive calls, how do I go through and capture the return value of malloc? Because I call malloc, that goes in x0. And then I go to the next context object, which completely destroys it. So how do I get it? So okay, this is a super gadget, but it doesn't really give us everything we would want. We need some way of putting it in a place that we can predict. And the problem with registers that get destroyed every single time we use a new context object is you can't, right? So we need to come up with a way that allows us to go through and actually capture the output of this somehow. So yeah, just sort of like, I have this here to go through to reference, but we have two options. We can either find a capture gadget or only use functions that use virtual addresses or pointers to pointers or whatever in regions that we can predict, right? So again, I assume we have a pretty powerful, reliable read-write, maybe only for a little bit, then it kicks off something else afterwards, but there is a read-write, so we know where some stuff is. Anything that would be called as a like a hop along the chain of context objects, I don't know where that's gonna be. So we have two options. Only use stuff that we can predict in memory, or come up with a capture gadget. So there are a couple that I kind of found, like some of them are kind of funny, where like if you call like malloc and then set the link register to be close, with the way that syscalls are implemented for close, it'll actually push that to the stack. So you can chain that together with like the link register pointing to it. That's also tricky though, because then as soon as you get there, it like, where do you go next, right? You can only control the link register once unless you like make a fake stack, which we're not gonna do, because I don't want to. There we go. But the other one that was really nice is pthread create and pthread join. So pthread create makes a pthread, and pthread join waits for one to end. And what's kind of cool about that is pthread create doesn't use like return values in the way that you might be used to in say like a Python function where you just return something at the end. It uses like effectively like a pointer to a region of memory where after this function succeeds, it'll write the thread ID, which means if I call pthread create and point it to a region of memory that I know where it is, basically like a rebased offset, then I can go through and predictably use that thread ID, which is very nice. The second one is if I set the link register for whatever function that I'm using to pthread exit, then it'll go through and write the return value in a predictable region of memory. Actually, so let me rephrase that. You won't be able, I don't think you can actually write that to a predictable region of memory, but it'll be accessible from pthread join if you give it the pthread ID. So what happens is pthread exit basically writes the return code, which is the last value of x0 from the last function. This is the return code inside of a like data structure that is reachable from the thread ID. And because the thread ID was written to a region of memory that I own and I know where it is, I can then call pthread join on that and then capture that argument or capture that return value. And the best part is I'm not even capturing it into a register, I'm capturing it into a pointer to a region of memory, which is 6, and now we have a capture gadget. So yeah, I kind of went over why this works, and I have this cute little animation for how it's actually going on. So, ding. I'm at the halfway mark. Cool, cool. Got to go a little faster. So, shit, I have like 50 slides. Okay. But do we kind of get a feel for, like, maybe not necessarily like the nitty-gritty of like how it's working, but just that there's this thing that allows me to go through and capture return values. And this gives us a lot, right? But it doesn't give us arithmetic. It doesn't give us conditional branching. But now we can go through and call a lot of stuff in sequence. Also, I'm just ignoring error checking because, you know, live on the edge. So, also, this is just a lot of work. Like, for those of you who have ever done CTFs, like, can't we just build a fake stack and get around? No, 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 no. We're not doing that. We're not going to build a fake stack because this is more fun. And also, ARM is adding shadow stacks. That's going to make forging that a little bit harder. So this is mostly just for fun. Again, I know this is not like a realistic thing, and this is just like tinkering around. And again, we're not using shellcode. So we need to do math, and we need to find some amount of conditional logic. So we're going to start with some math. And the way that I'm going to do this is I'm going to cheat. I'm going to go through, and rather than trying to implement any amount of math, I'm just going to write a bunch of lookup tables and have that be good enough. Because this is something that I can do in sequence reliably, right? Because right now what we have is I can call a lot of functions in sequence, and I can go through and capture return values. So as a like bootstrap phase of whatever my exploit is, I can just write an entire lookup table. That's kind of cool. So okay, I'll write like an addition lookup table of 256 by 256. And every single entry in that table is just going to be the sum of I and j. And this makes it like pretty straightforward to implement. Now, I need somewhere to put this all. I just put it in a file because it was easier. And like beyond this too, like you can like reliably predict file descriptors, or we can use the capture gadget, but I can just open a bunch of file descriptors and just write lookup tables. So at this point, we're like way beyond the point of Turing completeness. Or I guess there's no beyond the point. We have Turing complete, we're good. We have lots of things in here that are all independently Turing complete, that's what I mean. So yeah, we're gonna use a file, and then we're gonna constantly use pread and prewrite. And because we have this capture gadget, again, we can predict what the file descriptor is going to be and just rebase accordingly. So cool. Now, how do we actually go through and like, I don't know, like use this? Because there's one thing that I'm kind of overlooking. I need to be able to index into this lookup table, right? So I want you guys to think about that a little bit. So right now I can write the lookup table, I can read inside of it, but how do I like implement add, right? Like, yes, I know that like heuristically we're like, okay, like you have the I, you have the J, and you go to I, J, and that's the addition of I and J. This is obviously modulo 255, right? Not doing, you know, you can implement carries just as easily, right? Like the same way you would build like a full Adler, or you just keep going and stacking them. So, okay, think about the indexing piece, because I haven't explained that yet, and we'll come back to that. But just for now, trust me, bro, we can do this. Specifically, we can do the index operation right here. So more generally, we can write any lookup table we want, which is also kind of cool. So we can build circuits, we can build full programs, like we're kind of in business now. So, all right, how do we build the lookup table? Just for I and 256, for j and 256, what's the value of the function you care about? And big bang boom, you're good. So how do we get the index? And this is going to be an interactive point now, all right? I want everyone to participate. We're going to do Pictionary. So one of my favorite pastimes is taking, because I'll Google man pages instead of just typing man whatever it is. I'm one of those people. And I love looking at the Google image results because it's great. So we're going to start. What is this? Man, exit. All right. Man, elf. Man, read. Man. Okay, so yeah, that's it. Man swap. So obviously when doing this, I was like, shit, I need something that lets me swap a byte so I can use it to index, because there's no like shift operation. So I'm just like scrolling through like object dump of libc, and I'm like, what the hell is swap? So yeah, there's an operation called swab, which is actually kind of perfect for this. It's like the perfect function for like, it's exactly what you need in order to do like indexing into lookup tables, and actually didn't even bother to check like the right use for it. Like I think that's probably what it's used for, but I didn't know what it was. So yeah, you can go through and with 2 mem copies and a swab, index into the file descriptor table lookup thing, right? We write all the file descriptor, we write all the lookup tables to the file descriptor, which then just we use to index. So now we have functions we can call with capture. Now we have a way to index into it, and we're basically good. So, okay, what is the sound of a drowning statistician? Log, 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 log. What is the sound of a drowning FPGA? Lut, 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 lut. It's a great joke. So this is how swab works. It just does exactly the index operation that we need. So that's pretty useful. Okay, so we just solved arithmetic. That's pretty cool. What else? Well, we need some amount of conditional logic, right? So I need if A, go to context A, if B, go to context B, right? So what are we going to use? We're going to use another lookup table. I'm going to basically have a like table of context objects that are at different offsets, and based on the conditional logic of the argument that is passed, it'll jump to the offset that has the context object that corresponds to that logical branch, right? So yeah, it's just the answer to all this is lookup tables. So, all right, how do we do runtime branching? The exact same way that we did lookup tables. You build a table of context objects, rebased for whatever your scratch space is, and you're off to the races. So, okay, yeah, branching's not that bad. Not nearly as bad as some of the other stuff, I think. And I have many more slides, but I think I'm actually in good shape this time. So, okay, what about loops? You basically do the same thing, but just sort of expand it out. You need to go through and have like a context object that jumps back to a context object. So you just need it to be circular in some way. And what about multi-branches? I mean, there are a lot of ways of speeding this up. You could build another table. You can have like multi-indexes, but just like if I can do like pairwise branching, you can just do pairwise, then the next pair, then the next pair, then the next pair, and it just works, right? So there's a bit of an optimization you can use with a separate lookup table for this, but it's fine. Okay, so now we have everything we need to start programming, which is very cool. So now we're going to go through and try to build a compiler. So is this Turing complete? Here's a little Turing machine. I'm going to go through and run it. That's the input. I'm just going to add 1 to it. And this is what a demo looks like. You build it, you run it, and it prints the thing. So that wasn't very exciting. So let's go ahead and actually run this with BPF trace running. So I'm going to go ahead and run it. Nothing happens. Still nothing super interesting. This is like surprisingly fast actually for what it's doing. And now I'm going to log every single time we call setContext and what the context pointer is. And it's vomiting out a bunch of swabs and setcontexts. So yeah, and again, like there are some details here where you need to go through and like build out this table of lookups. But again, that's just, you know, right. Yeah. Then you got to go through and like build out all these like values that you rebase. And it's, you know, by the way, when I say rebase, I'm pretending that I have some scratch space. I know the virtual address of it. I'm going to stick a bunch of objects in there. All of those are offsets relative to a base. I know that base. I rebase all those offsets, and we're good to go. Now I know the absolute virtual address of all of these little things, because I'm using memcopy a lot, right? So I have to know the actual virtual address, not just the offset. So, okay. Now we're at a point where we need a bug. So we need to go find something that gives me a read-write. We need to then turn that read-write into a weird machine, and then we're going to start building programs that run on it. I'm going to leave the read-write as an exercise to the user, and also maybe like let's use C and C++, because imagine like trying to get someone to learn another DSL, and that's just not going to happen. Everyone writes in C and C++. I mean, I like Rust, but everyone uses C and C++, so all your tooling needs to work with C and C++. Obviously, we can't get all of C and C++, but we can get like enough of it where it's okay. So we're going to build a compiler. I don't know how to build a compiler. I read the Dragon book a while ago. I don't know what a dominator tree is. Please do not explain it to me. I'm not interested in learning. And yeah, I'm just going to ask Claude to like combine all these little basic building blocks, and then it's just going to kind of work. So to keep this grounded, one of the things that I want us to all have kind of as a picture in our head you take an ELF file, you run that ELF file, and it does some stuff. But there's a lot of steps that happen in between, like doing ./a.out and when hello world shows up. So namely, the loader runs. So it jumps into the kernel, it memory maps all the segments, it then spits it back out to user land. The linker or the dynamic linker will go through and fix up all the offsets, and then it'll jump to the entry point. In the context of an exploit where you're running it with a read-write or some sort of exploit, now all of a sudden the loader is running the exploit. So you can kind of think of it as like a generic, like templated, like, I don't know, COPr, and then instead of like a generic for like a type, you would just say exploit. And then whatever that exploit is, it's responsible for doing all the like mapping of segments, dealing with rebasing, and then jumping to the entry point. So to keep this concrete, I have a little dummy program called vuln server, which spits out some information to give us a leak so we know where stuff is. It gives us a little scratch space so we can work around with it, write some data to it with the write, and then I give us a jump. So I get one setcontext call. Now, this might sound like cheating, but again, you can override like stack check stuff or exit handlers, and it'll still jump there anyway. So this is just making the development a little bit easier. And one fewer thing can go wrong. Oop, I spelled, wait, no, I did spell concrete right. OK, cool. So this is the server. It doesn't really do that much. The big thing is you send it an R, you read some memory, you send it a W, it writes some memory. Once you're ready to go, you do jump, and then it just jumps to the first context object. So yeah, this is the API that our vulnerable server is giving us. And we're going to go through and implement a loader specifically for it. Like, this is kind of like what it's all been building up to. We need some sort of executable file format and something that resembles a loader. And then we're going to staple that together to target the vulnerable server, which is, again, just a made-up thing. So yeah, I think I just actually said all of, oh, I did do a little generic thing there. That was good. So yeah, I could go through and build load COPr, and then I just swap it in for whatever the exploit is. And this is kind of me like popping off again, but I don't think you're going to be able to do this super generically, because I think that getting like super, super reliable arbitrary read writes like going forward is going to be just probably a lot harder. So you're probably going to have to redo this from the ground up for every single new thing. But that's also not that big of a deal because, again, if you ask Claude nicely, it'll go through and just write you an LLVMIR parser. So that's cool. So we kind of got a feel for what the loader looks like, but the loader needs to load something. And what is that something going to be? Well, for one, like, anyone here want to pop off about large, just shout out, why do we have elves? Like, what are some features of an elf that makes programming easier? The PLT, that's one. You don't need to know where stuff is at compile time. Yeah. What else? Relocations, that's awesome. I don't have to know what my base address is because I'm not going to know until runtime, right? It basically lets you deal with things at runtime that you won't know at compile time, right? So whatever our executable file format is, or just calling it a COPr, I'm just basically copying ELF. I'm copying the idea of segments. I'm copying the idea of the text section, which is just all the context objects. And by the way, one detail that I left out, every single context object needs its own stack, which is kind of annoying, but it's not that big of a deal. And also, if it's referencing something that uses a memcopy, that's at an offset from our scratch space or our workspace. We need something to rebase that, right? We need something to do relocations. So we need to put all those relocations in a place where the loader can parse them and then apply them. So, all right, we're going to build our own version of the global offset table. We're going to add our own version of the PLT. How are we going to deal with threads? Also, how do we run big programs? So the global offset and the global offset table with the PLT, not that bad, right? We just store a list of offsets and walk that list of offsets and then just change them. Threads are kind of annoying because if you just call pthread create and you're using the same lookup table that somebody else's and you call pread or pewrite, you might stomp over what it's using. So you have to make a separate context chain for every single thread. And then I guess like talk to each other using shared memory or something. That sounds annoying. What about big programs? Like, I actually did try compiling Doom and unfortunately couldn't get it working. But it was like, I think like 1 million context objects, which was like a couple of gigs of memory. you're probably not going to get a couple of gigs of scratch space. So like maybe I should go through and write like a stager for this, right? Like what would that stager look like? Well, mmap, big region of memory, connect out on a socket, grab everything, rebase it, and basically ship the loader inside of the bootstrapper. So, okay, threads are kind of annoying and really tedious, but you can solve this problem. Likewise, bigger programs, but it does get super slow. I got to the menu screen in Doom and then it crashed and I just gave up, but maybe at some point. So we're gonna go through and build a programming language on top of all of this by just using C, compiling to LLVM-IR, and then just lifting it. So yeah, we're going to go through and take C and put it in some sort of state that it's usable. Then we're going to go through and take advantage of all of this machinery that we've built up and basically just map out every single LLVM-IR operation to something that we already know how to do. And because we have arithmetic and conditional logic and function calling with capture, we're golden, right? So, okay. I don't actually want to write any of that. That sounds hard, and I don't want to learn LLVM-IR. And you can ask Claude really nicely to do it. Now, if you ask Claude to go through and build you a weird machine, it won't. But if you give it a list of operations that map to arithmetic, conditional logic, calling arguments, and getting the output, it's pretty good at wiring it up. What exactly did it wire up? All this crap. And that's okay. There's actually some more in there, too. But this is enough. Like, all of these little operations are generally enough to run most C programs. You can even build structs on top of this. Pure virtual functions was kind of tricky, but and I don't think it's actually fully working. But you can use most of C and C++. Now, exceptions are kind of annoying, and like runtime information is kind of annoying, but you don't need all that, right? So, okay, what is the loader actually going to do? It's going to take our LLVM-IR lifted program and then just throw it at the vulnerable server, right? So it needs to go through and basically parse out. The server just leaks some information, gives us the layout of what a context object is, because that changes from glibc version to glibc version. We find some hard-coded offsets for some functions that we'll need. So this is not ideal. You need to know some offsets. But again, we'll have the global offset table PLT thing, and we can go through and just leave a bunch of thunks empty, and then as a part of loading, populate them. What do we populate them with? We just keep calling dlsim and just keep writing that target value to the next offset in our little PLT table, right? So yeah, the loader will read some memory, rebase our COPr program, write it to the scratch space, and then trigger the set context jump that kicks all this off. So I get a big read, a big write, and one jump. Seems like a pretty reasonable thing to have. The scratch space, maybe not so much, but again, you could go through and stage this and make it smaller and code golf it, and I could not be bothered. So, okay, what offsets do we need to get started? Well, we need start context, which is luckily normally at a fixed offset from start context. So we need start context. We need dlsim, pthread create, pthread join, pthread exit, and memcopy. I feel like we could probably get away with like dropping one or two of these by using, the auxiliary vector, but again, I could not be bothered. This seems like a reasonable amount of offsets to use, then we can just find the rest. So what is that global offset table going to look like? I'm running out of time. A bunch of different entries in a table that we memcopy the real virtual address to after calling setcontext into pthread create with pthread exit as the link register. Next one being pthread join, understanding the exact virtual address of where that pthread ID was written. Now, the one thing to keep in mind is this is a little racy, so don't do super long running things. But what's nice about pthread join is it'll just wait for it to finish, right? So it's pretty safe to use, actually, which is very nice. So yeah, not that bad. So now we have a usable global offset table. That's pretty neat. What else do we need? Well, we got to actually build a format and write a loader. And again, I just copied elf, like straight up. In fact, I think I actually copy and pasted some stuff from elf.h. And it's just, you have some relocations, you have your text, which in this case is just a bunch of context objects, and then you let the loader do its thing. So what does the pipeline for this actually look like? You take your C program, you spit out some LLVM-IR, then you feed that into the specific COPr LD linker, and then it'll go through, take that, figure out all the rebasing it needs to do, then interact with the vulnerable server, do a bunch of reading, rebase the actual executable, write the executable to the scratch space, and then trigger the set context, which triggers the jump. And now you have this super long chain of set context, swabs, and pthread creates, pthread joins, and pthread exits. So what does this actually look like? Again, it's not super, it's just a shitload of start context and set context and everything else, but you can ping, you can ask it to tell a joke, you can go through and have it echo text back, and you can go through and use it like a shell, right? So great, you can do cat etc password entirely in context objects. So, okay, should you use this in real life? No, it's extremely slow. I mean, the idea of creating a thread for every single function you want to call seems kind of bad. You got to know a lot of offsets, which is bad. Your read-write needs to be super reliable and repeatable, which is also bad. It's really, really slow. It's really, really big. And it's going to be really brittle in between like different versions of the same system. Also, it is a major pain in the ass to debug. But if it's all you have, I guess it's better than nothing. So, all right, what about on like other systems that are not Linux? So on Windows, you have NT-continue and a couple of other bootstrap, like there's a start context like gadget in there. So I think this will work, but I haven't actually checked, and there's probably some sort of like Windows like set BS in there that makes it harder, but probably not impossible. On Android, there actually is set context and start context. It's just not called that, so happy hunting. And on Apple, I think there's like a ton of options, but you need a task port, and getting a task port's like a task control port's like really, really hard. Also, there's probably some BS with like Objective-C and GCD, but again, could not be bothered. So, finished early. All right. Well, any questions? No, I was totally clear. Yeah. Yeah. Summer at DEF CON this year, keep an eye out for it. You're going to have to reverse engineer it. Like, you know the like Mobfuscator CTF challenges? There's one where it's reversing this. Yeah. I'm super deaf, by the way.
Sorry. So this requires that you like have your program. Sorry. Your program is a bunch of context objects that you write beforehand, right?
Yeah.
So I didn't really understand the part where you were talking about conditional like branching. How does that cope with the fact that you have to like predetermine the contexts and the registers that goes in each context? Like how do you dynamically assign the registers?
Right. So I'm not dynamically assigning registers. I pre-prepare context objects at fixed offsets, and then when a function does a conditional branch, it does a comparison and adds that offset to what the context object is going to be next. If it's true, that offset is 0. If it's false, it's the size of the next context object. So you can't do dynamic conditional logic where if I wanted, well actually I built an interpreter so technically you can, but you can't at compile time do this. You need to pre-stage every single path that the conditional object might take as a separate context object. Then when you do the index into like by a swab into a lookup table, it basically adds that to the context object that was rebased at load time that you're going to jump to. And if it's true, it's going to go to X. And if it's false, it's going to go to X plus size of context.
Okay.
Does that make sense? Or
Essentially skipping context.
that's right.
Yeah. That kind of makes sense. Another thing is like this to make an exploit with this, you need to have a runtime in the vulnerable system, like a coroutine runtime that uses this like ulink thing, right?
Or you need a bootstrap trampoline. So I'll spoil one thing. I think it's like RT like sigret basically gives you start context. So you need both context switching and something that allows you to sort of stitch these together in like a CFI friendly way or a VTI friendly way. And like SROP is like a well-known thing, and like a lot of the same ideas apply here as well.
Okay, so by the trampoline, if you don't have like a ulink thing where it like automatically will just hit the next context,
Yeah.
you have to like set the register to a trampoline or something?
That's right, yeah.
Okay. All right.
Going once.
Love it.
Cool. All right. Thanks, y'all.